Hello everyone, I am Rutav Shah, a summer scholar at Carnegie Mellon Robotics Institute, working under the guidance of Dr. Vikas Kumar, Yunzu Lee and Dr. Abhinav Gupta. I'll be presenting my summer work on generalization and reinforcement learning through representation. Recently, we have seen huge progress in reinforcement learning ranging from Go to real-world applications in robotics. However, most real-world successes in robotics are still limited to laboratory, instrumented conditions. What we want to achieve is to learn without these environment instrumentations in a more natural condition. However, this demands to learn directly from the information received from onboard sensors, which is filled with information irrelevant to the task in hand, like background, clutter, etc., and is also quite high-dimensional, which makes the policy learning sample inefficient and hence learning directly in real world even more difficult. A common technique is to learn a low-dimensional representation of this high-dimensional input information received from the onboard sensors like the camera. The relevant question here is how to achieve this low-dimensional representation, what properties it should have. An ideal representation is one that pays attention to the important aspects of the task and ignores the irrelevant information, learns semantically meaningful representation that helps in improving the generalization performance of the policy, and also is low dimensional so as to improve the sample efficiency of the policy learning. The key idea of our approach is to learn a robust tense descriptor from an input image in a completely unsupervised manner. The descriptor learns a semantically meaningful representation. For example, in the given image, different parts of the sugar box is represented by a distinct color in the descriptor space, which is robust. Now this descriptor learned is also robust to large variations. Next, we use a feature extractor to extract a low-dimensional representation from the descriptor space. Finally, a policy learning phase which solves the task efficiently using the representations acquired. It is important to note that we freeze the weights of the tense descriptor and the feature extractor during the training of the agent. Firstly, we benchmark the performance of our approach, DDRL, in blue on the hammer task of adroit dexterous manipulation benchmark. We notice that our approach, again in blue, is more sample efficient than two state-of-the-art approaches, RRL in orange and firm in green. Interestingly, we observe that the performance is even better than DAPG state in red, which uses the privileged state information. Now, similar to RRL, in order to test the robustness of the pipeline, we evaluate the performance by introducing various visual distractors like changing lighting conditions, introduction of a random object into the scene, etc. during test time, and observe that our approach, which is in yellow, consistently outperforms other baselines. This suggests that the policy is learned sample efficiently and is robust to various visual distractors. Now, in order to better test the generalization performance, we train the network on a set of semantically similar tools, that is, ratchet, spatula, knife, screwdriver and turner, where the task is to pick up the tool and reach to a target position using the 24 degree of freedom adroit hand. While during test time we expose the model to a completely new tool, that is hammer, and measure the performance. First, we visualize the descriptor learned on the set of training tools and use the same model to visualize the qualitative performance on a completely unseen tool. We observe that the model transfers well even to the hammer object which it has never seen before. For example, the neck of all the tools are in the same space of whitish pink as seen in the visualization. Finally, we measure the performance of the policy on seen in blue and unseen in red and notice that the policy performs very well on the new tool, which is hammer. Interestingly, the performance on the unseen tool is slightly better than that of the average performance on the set of 5 seen tools, mainly due to the fact that one of the tool fails sometimes due to the large variation in the geometric shape of the handles. This demonstrates that the dense descriptor learns semantically meaningful representation which in turn helps in better transfer of policy to a completely unseen but semantically similar tool. In the end, I would like to thank all the sponsors and mentors without which this would not have been possible. Special thanks to Dr. Rachel and Dr. John. Lastly, to all the cohort members of the RIS program, thank you all.